From the moment human beings first gazed at the skies, light has been both guide and mystery. It floods the world with clarity, yet its essence has always seemed to escape complete understanding. For ancient people, light was divine, something carried by the sun across the heavens each day and extinguished each night. For philosophers, light raised questions that challenged the very nature of existence. Was it a stream of particles, tiny seeds of illumination that traveled across the void? Or was it instead a vibration, a wave spreading outward, like ripples on a pond? Centuries of debate followed, as some thinkers swore that vision was made possible because light was emitted from the eyes, while others insisted that objects themselves gave off something that traveled to us. In every case, light remained the thread binding together how we saw, how we measured, and how we made sense of the cosmos. By the 17th century, science began to take its first careful steps toward truly measuring this elusive phenomenon. The Danish astronomer Ole Rømer noticed something extraordinary in the motions of Jupiter's moons. He found that the predicted times of their eclipses did not always match what he observed. At first glance, it looked like an error, a miscalculation, or a flaw in his telescope. But Rømer realized the real explanation was far more profound. The difference came from the changing distance between Earth and Jupiter as they orbited the Sunday. Light, he reasoned, must take a finite time to travel that varying distance. From this insight, Rømer became the first to estimate the speed of light. Though his numbers were not exact by modern standards, the idea itself was revolutionary. Light was not instantaneous. It had a speed, and therefore, it could be measured. This marked the beginning of a journey that would span centuries. Later, in the 19th century, the French physicist Hippolyte Fizeau attempted to measure this speed more directly. He devised an ingenious experiment involving a rapidly rotating toothed wheel and a beam of light reflected from a mirror several kilometers away. By adjusting the rotation of the wheel, Fizeau found the precise point at which light passing through one gap would be blocked by the next tooth upon its return. From this delicate balance of timing, he calculated the speed of light with remarkable accuracy for his time. His fellow countryman Léon Foucault improved on this method with a rotating mirror apparatus, pushing the precision further still. Then came Albert Michelson, whose life would be dedicated to refining these measurements. In the late 19th century, Michelson constructed interferometers of extraordinary sensitivity, capable of detecting tiny differences in the travel time of light beams. His work not only measured the speed of light with ever-increasing accuracy, but also prepared the foundation for experiments that would later shape modern physics itself. It is no exaggeration to say that Michelson's efforts helped elevate the speed of light from a curiosity into one of the cornerstones of science. By the 20th century, the pursuit of precision had reached new heights. Scientists realized that the very definition of length could be tied to light. In 1983, an international agreement redefined the meter, not by a physical object, not by a bar of platinum stored in Paris, but by the speed of light itself. The meter became defined as the distance light travels in vacuum in a tiny fraction of a second. This definition was not only elegant, it was absolute. It declared that the speed of light in vacuum, denoted by the symbol c, is exactly 299,792,458 meters per second. It was no longer just a measurement. It was the foundation upon which our system of measurement rested. Why elevate this particular number to such a sacred status? The answer lies in the universality of c. Across every experiment, across every observation, the speed of light revealed itself as unchanging. Unlike the strength of gravity, which varies depending on location, or the pull of a magnet, which depends on distance, the speed of light remained constant under all circumstances. This constancy meant that light was not just another player in the theater of nature, it was the stage upon which the play unfolded. Equations describing electromagnetism, relativity, and even the structure of the atom all required c as their anchor. Remove it, and the framework collapses. And yet, science never allows even its most trusted assumptions to go unquestioned. To declare something constant is to invite the challenge. Has it always been so? Could it, under circumstances beyond our current reach, vary ever so slightly? The speed of light sits at the heart of physics, but the true heart of science beats with curiosity and doubt. For every constant we accept, we must remember that it is only as firm as the next experiment allows. As we move deeper into this story, we will see that the journey of light is not simply about numbers or measurements. It is about how humanity dares to measure the immeasurable, to test the very limits of the universe, and to confront the possibility that even the most secure truths may one day shift. Light, the measured constant of nature, is not only a physical phenomenon, it is a symbol of the ongoing quest to understand reality itself. The constancy of light may feel obvious today, but it was anything but certain for the thinkers who first struggled with the question. For centuries, even after Römer's insight, debates continued over whether light had a finite speed at all. Some argued that light moved instantaneously because they could detect no delay when striking a match or glimpsing a star. The sheer magnitude of the speed made it difficult to measure by everyday means. To claim that light required time to cross space was to claim that distances within our own solar system translated into minutes of delay. Such an idea required patience and careful reasoning, qualities not easily sustained when faced with an effect so far removed from ordinary experience. But gradually the evidence built. Each experiment confirmed the earlier ones, refining the numbers, correcting errors, sharpening the accuracy. With Fizeau and Foucault came laboratory measurements that removed reliance on celestial mechanics and placed the question firmly in human hands. By the end of the 19th century, there was no longer serious doubt. Light was fast, astonishingly fast, but not infinite. It had a speed, and that speed could be pinned down with ever smaller margins of uncertainty. This shift from speculation to precision was more than a technical triumph. It signaled the maturing of physics itself. To measure light was to touch the very rhythm of the cosmos. Every reflection, every refraction, every glimmer of starlight obeyed this universal pace. When Maxwell formulated his equations of electromagnetism in the 1860s, he discovered something even more profound. By combining electricity and magnetism into a unified theory, he found that electromagnetic waves would travel through space at a speed predicted by the constants of those forces. The number that emerged from his calculations matched the measured speed of light. Suddenly, light itself was revealed to be an electromagnetic wave, a ripple in the fields that weave space together. It was not only that light had a speed, it was that the speed of light was built into the very fabric of the equations governing nature. From that moment, the speed of light acquired a new significance. It was no longer merely a property of illumination, no longer just a number that could be written in tables. It was the messenger of a deeper unity, binding together electricity, magnetism, and optics. Every spark, every lightning bolt, every flicker of a candle flame spoke the same language, a language inscribed in Maxwell's equations. And at the center of that language was C, a constant not invented by humans, but discovered as the pace of reality itself. Michelson, working in the late 19th and early 20th centuries, understood this importance. His interferometers were not only about precision for its own sake, they were instruments designed to probe the deepest questions of motion and light. Together with Edward Morley, he conducted what became one of the most famous experiments in science. At that time, many believed that light waves must travel through some invisible medium, an ether that filled space. Just as sound requires air and water waves require water, surely light must need something in which to ripple. Michelson and Morley set out to detect the Earth's motion through this hypothetical ether. They reasoned that if Earth moved through the medium, the speed of light should vary depending on the direction measured. But when they turned their device in every orientation, the result was the same. No matter how they tested it, light traveled at the same speed. The ether could not be found. This null result was more than a disappointment for ether theorists. It was a revelation. It told scientists that the speed of light was not relative to some unseen background. Instead, it seemed to be absolute, the same for all observers regardless of motion. It was as though nature itself insisted that light could not be measured differently depending on perspective. This stubborn constancy set the stage for the most radical rethinking of physics the world had yet seen. At first, the conclusion felt unsettling. If light refused to change its speed depending on the observer, then something else must give way. For centuries, the foundations of motion had been laid down by Galileo and refined by Newton. Velocities were supposed to add together. A moving ship launched a cannonball, and the ball's speed relative to the shore was the sum of the ship's speed and the ball's speed relative to the ship. Why should light not obey the same rule? If you moved toward a beam, should you not measure it to be faster? If you moved away, should it not seem slower? Yet Michelson and Morley's experiment defied that logic. Light was unmoved by your motion. It traveled at sea regardless. This puzzle pressed heavily on the scientific mind. The stage was set for Albert Einstein, who in 1905 would take the bold step of making the constancy of light not a problem to be explained away, but a principle to be embraced. But before we reach that chapter, it is worth reflecting on how extraordinary this shift truly was. For the first time, a speed was elevated from measurement to law. It was not just another number like the velocity of a bullet or the orbit of a planet. It was a ceiling, a limit, a universal constant that every observer must respect. By defining the meter in terms of this constant, science acknowledged its central role. The redefinition in 1983 sealed this idea for all of modern science. Now, rather than relying on artifacts of metal or stone to mark distances, humanity entrusted its system of measurement to the unwavering pace of light. Every laser experiment, every fiber optic signal, every reflection within a microscope became a quiet confirmation of this choice. The constancy of C became the heartbeat of measurement itself. And yet, one question continued to whisper beneath the triumph. Was this constancy an ultimate truth of the universe, or merely an approximation that held within the limits we had so far observed? Could it be that under other conditions, in other epochs of the cosmos, the speed of light might shift, even slightly? If so, what would that mean for our understanding of space, of time, and of the laws we hold so dear? The story of light as a constant is as much about philosophy as it is about measurement. Each refinement in our ability to pin down its speed forced humanity to confront deeper questions about the nature of reality itself. To say that light has a finite and constant speed is to say that time and distance are not merely human inventions, but woven into the very structure of the universe. Whenever light travels, it reveals that structure, tracing out the architecture of space and time with perfect regularity. Consider for a moment what it means for light to be unchanging. Imagine standing on a shoreline, watching waves crash against the rocks. The waves can be faster or slower depending on the wind, the tides, or the depth of the sea. But light does not behave this way. Its speed does not depend on the source that emits it, nor on the observer who receives it, nor on any invisible ocean through which it might move. It stands apart, refusing to obey the intuitions that work for every other kind of motion. That refusal is not a flaw in our understanding. It is a clue, a beacon guiding us toward a new vision of physics. Even in the 20th century, when the constancy of light was being solidified into the very definitions of measurement, there were those who struggled to accept it. After all, it went against centuries of thinking. Newton had taught that space and time were absolute, a stage upon which events unfolded, but which themselves remained untouched. If the speed of light was fixed regardless of motion, then either Newton's stage was not absolute, or our very sense of how time and distance worked had to be reconsidered. Both possibilities were unsettling. And yet, as experiment after experiment confirmed the result, the scientific community had no choice but to face this new reality. This is the true power of science. It does not cling to tradition for comfort. It does not elevate authority above observation. Instead, it bends, however reluctantly, to the verdict of nature itself. Romer's eclipses, Fizeau's wheel, Foucault's mirror, Michelson's interferometer, and the modern atomic clocks of our own era all speak the same message. Light travels at a constant speed, and that constancy, more than any authority or doctrine, is what forces physics forward. By the late 20th century, the question of how to define length and time reached a logical conclusion. Scientists could no longer allow the meter to be tied to a metal bar that might expand or contract, nor could they let the second remain linked to the rotation of Earth, which drifts ever so slightly with tides and geological processes. Instead, they anchored both to unchanging natural processes. The second was defined by the vibration frequency of cesium atoms. The meter was defined by the distance light travels in that time. With these choices, humanity built a measurement system not on fragile earthly artifacts, but on the immutable behavior of the universe itself. This anchoring of our measurements to C is not a trivial act. It means that whenever you measure a distance in meters, you are in effect measuring how far light would travel in a fraction of a second. Every ruler, every tape measure, every architectural plan is connected, however indirectly, to the unwavering pace of light. The constancy of C has become the quiet foundation beneath our daily lives, whether we notice it or not. Still, questions remain. If C is so constant, why does science continue to test it? The answer is simple but profound. A constant is only as strong as the experiments that verify it. History is filled with ideas once thought unshakable that later yielded to new discoveries. To assume constancy without testing would be to abandon the very spirit of science. And so, the speed of light continues to be measured with ever greater precision. Each experiment, a silent challenge to the universe. Will you reveal something new, or will you remain as steadfast as ever? So far, light has remained steadfast. Within the limits of all our instruments, C has not changed. Across laboratories, across satellites, across astronomical observations stretching back billions of years, no variation has been confirmed. The constancy holds. And yet, the mere possibility that it could one day falter keeps the scientific imagination alive. What would it mean if C were not the same everywhere or everywhen? How would our understanding of time, of space, of causality itself be reshaped? These questions hover at the edges of modern physics, reminders that even the most trusted truths must remain open to scrutiny. In the end, light is more than illumination. It is the pace of reality, the standard by which we measure not only distance, but also our own understanding of the cosmos. To speak of light as a constant is to acknowledge that there exists in nature something that refuses to bend, something that anchors the universe in order. But it is also to accept that our knowledge is always provisional, always ready to be tested again. This is where our journey truly begins. We have walked through the history of how light was measured, how it became elevated from curiosity to cornerstone, and how it now underpins the very definitions of length and time. But the story does not end here. For the true revolution arrived when Einstein asked the daring question, what if the constancy of light is not just a number to be measured, but a principle to be embraced? If light always moves at the same speed, then space and time themselves must adjust to accommodate it. With that leap, physics would be transformed forever. And so, as one chapter closes, another opens. From the ancient puzzles of philosophers to the experiments of the 19th century, light has guided us forward. But now, in the 20th century, it will take us further still, leading us into the strange and beautiful world of relativity, where time slows, lengths contract, and energy and mass reveal themselves as two faces of the same truth. In the year 1905, Albert Einstein was a young man working at the patent office in Bern, Switzerland. He had not yet become the most famous physicist in the world. To his colleagues, he was an ordinary clerk, reviewing technical documents. Yet in his mind, ideas were colliding in ways that would alter the course of science forever. Among those ideas was a bold confrontation with the stubborn constancy of light. While others struggled to reconcile the findings of Michelson and Morley with the laws of motion laid down by Newton, Einstein did something different. He accepted the constancy of light as a fact and asked what the universe must be like if it were true. This was a daring move. At the time, most scientists sought ways to explain away the results of the interferometer experiment. They imagined that perhaps the ether existed but behaved in strange ways, or that instruments were somehow compensating for Earth's motion. Few were ready to abandon the bedrock of Newtonian physics. Einstein, however, was not weighed down by authority. He trusted the principle that nature itself had the final word. If every experiment confirmed that light always moved at the same speed, then perhaps it was not the experiment that was strange, but our assumptions about space and time. In his paper that year, later known as the special theory of relativity, Einstein presented two simple postulates. The first was that the laws of physics are the same in all inertial frames, meaning for any observer moving at a constant speed in a straight line. The second was that the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the source. From these two statements, he derived consequences that seemed at first to defy common sense, but that have since been confirmed by countless experiments. If light's speed is always the same, then time cannot flow identically for everyone. A moving clock must tick more slowly relative to a stationary one, a phenomenon we now call time dilation. Distances too must bend under this rule. A moving ruler appears contracted in the direction of motion, a phenomenon called length contraction. These effects are not illusions, not tricks of perception, but real consequences of the geometry of space and time. Relativity tells us that what one observer considers simultaneous events, another may not. The concept of simultaneity itself, once taken for granted, dissolves under the light of Einstein's reasoning. This shift was revolutionary. For centuries, people had believed in a single universal time that flowed steadily like a river, the same for all observers everywhere. Relativity shattered that image. It replaced the river of time with a flexible fabric, where intervals stretch or compress depending on motion. The faster one moves, the more time itself bends, ensuring that light's speed remains constant for all. Einstein's second great insight in that paper was the relationship between mass and energy, encapsulated in the equation E equals mc squared. This equation did not appear fully formed in the first paper, but followed soon after as a natural extension. It showed that mass could be seen as a form of energy, and energy as a form of mass. The speed of light, squared, served as the conversion factor. Once again, c was not merely a speed, but a universal bridge between two seemingly different aspects of reality. For ordinary life, these effects are hidden. A car traveling down a highway at 100 kilometers per hour experiences time dilation so tiny, it is immeasurable without extremely sensitive instruments. But as speeds approach that of light itself, the differences grow dramatic. For particles in accelerators, time slows so much that unstable particles live far longer than they would at rest. For astronauts traveling near light speed, the journey would last only years for them, while centuries could pass on Earth. Relativity opens the door to these extraordinary possibilities, all flowing from the simple act of declaring that light speed is constant. At first, the world did not know what to make of these ideas. They seemed abstract, even absurd. Yet the mathematics was clear, and as technology advanced, experiments confirmed them again and again. Muons created high in Earth's atmosphere live longer because they move at near light speeds, reaching the surface when they should have decayed long before. Atomic clocks flown on airplanes tick differently from those left on the ground, exactly as relativity predicts. The universe, it turned out, was stranger than common sense had ever allowed, but far more coherent when viewed through Einstein's lens. In this way, Einstein transformed c from a measured constant into a principle of nature. It was no longer simply a number, no longer just a velocity to be tabulated. It was the foundation of a new physics, one that required space and time themselves to bow in order to preserve its constancy. With that leap, relativity was born, and the old absolutes of Newton were left behind. Einstein's leap of imagination was not conjured from nothing. He had grown up, immersed in the puzzles of light, fascinated by how electromagnetic waves behaved. As a teenager, he often pictured himself chasing a beam of light across the void. If he could somehow keep pace with the wave, what would he see? Would the wave freeze in front of him, its oscillations suspended in time? Maxwell's equations did not permit such a thing, for they described waves that always moved forward at the same speed, regardless of who was watching. From this youthful thought experiment came a profound discomfort, one that lingered with him until he found a solution. The answer was relativity itself, a framework in which no observer could ever catch up with light, no matter how fast they ran or how powerful their engines. In the years leading up to 1905, physics was at a crossroads. The mechanical worldview of Newton, with its absolute space and absolute time, had guided science for centuries. But cracks were showing. The failure to detect the ether gnawed at theorists. The unity of electromagnetism hinted that old assumptions could no longer hold. Einstein's willingness to discard the ether and to embrace constancy as a principle set him apart. Where others saw contradiction, he saw clarity. His first postulate, that the laws of physics are the same in all inertial frames, might have seemed uncontroversial. Galileo himself had argued centuries earlier that the rules of mechanics are identical for sailors on a smoothly moving ship as for those standing on the dock. But Einstein extended this principle to all of physics, not just mechanics. Electromagnetism too must follow the same rules for all observers. His second postulate, that light travels at the same speed for everyone, was the radical part. Taken together, these postulates forced space and time to bend into a new geometry that later became known as space-time. The implications unfolded quickly. Time dilation means that moving clocks tick more slowly. Length contraction means that moving objects shrink along their direction of motion. But deeper still lies the relativity of simultaneity. Two events that appear simultaneous to one observer may not be simultaneous to another, who is moving differently. This was not merely a philosophical curiosity. It meant that the ordering of events, the rhythm of reality, could shift depending on the observer. The absolutes of Newton had given way to a flexible fabric that adjusted itself so that C remained untouched. For those trained in classical physics, this was deeply unsettling. How could time itself change depending on motion? Yet, experiment after experiment confirmed it. The mathematics of relativity was elegant, but its predictions were even more compelling. In laboratories, particles moving close to light speed behaved exactly as Einstein described. Astronomical observations of fast-moving stars and cosmic rays matched the same laws. What had seemed absurd in 1905 became unshakable truth by the mid-20th century. Among the most celebrated consequences was the equivalence of mass and energy. The equation E equals mc squared revealed that matter itself held vast reserves of energy, locked within its mass. Even a tiny amount of matter contained an enormous store of energy because the conversion factor was c squared, a staggering number when written out. This insight did not remain theoretical. It powered the sun, where nuclear reactions turned mass into light and heat. It powered humanity's most destructive weapons, the atomic bombs of the Second World War. It powered nuclear reactors that lit entire cities. Einstein had uncovered a truth so deep that it reshaped both science and history. But even here, the constancy of light was central. Without C serving as the conversion bridge, mass and energy would remain separate quantities, as they had for centuries. With C, they were unified, different faces of the same coin. The constancy of light was not simply a matter of measuring beams in laboratories. It had become the thread weaving together the most fundamental aspects of existence. Despite its radical consequences, special relativity did not discard Newtonian physics entirely. At everyday speeds, where motion is slow compared to light, Newton's laws remain an excellent approximation. Engineers building bridges, pilots flying planes, even astronomers charting planetary orbits can rely on classical mechanics without trouble. But at high speeds, when velocities approach c, the cracks appear. Only relativity can explain what happens when time itself begins to bend. In this sense, Einstein's theory was not a destruction of Newton, but a refinement. It revealed that Newton's framework was a special case, a subset of a broader and deeper law. Nature had not betrayed the old physics, but had shown it to be only part of a larger story. Light, with its unwavering constancy, had forced the expansion of that story. By the end of the first decade of the 20th century, Einstein's ideas were spreading, debated, and increasingly tested. Some resisted, unable to let go of the absolutes of space and time. Others embraced the elegance of the new vision. What united both sides was the recognition that physics could never be the same again. The constancy of light had upended assumptions so old they felt like common sense. Now, common sense had to yield to the verdict of experiment. The transformation that relativity brought was not only scientific but philosophical. For centuries, humanity had pictured the universe as a grand stage, unchanging and absolute. Time ticked forward like the steady beat of a drum, the same for all observers. Space stretched out like an endless grid, a fixed backdrop against which planets, stars, and people moved. These assumptions were so ingrained that they felt beyond question. Yet Einstein showed that they were not eternal truths but conveniences, approximations that broke down when confronted with the constancy of light. In relativity, the universe is not a stage but a fabric. Space and time are not separate entities, but interwoven into space-time. Motion through this fabric is not absolute but relative, always measured against the speed of light. And the speed of light itself, c, stands as the boundary that no material object can cross. It is the horizon of the possible, the limit that shapes the behavior of all things. At first, this seemed to suggest strange paradoxes. Imagine twins, one staying on Earth, the other traveling near light speed to a distant star and returning. According to relativity, the traveling twin will have aged less than the one who stayed behind. This is not a trick of perception, but a real difference, confirmed by experiments with particles and with highly precise clocks. Time itself bends to preserve the constancy of c. The universe does not break its rule. Instead, it reshapes its own fabric to obey it. Another apparent paradox arises when thinking about simultaneity. Suppose two lightning bolts strike opposite ends of a moving train. To an observer standing on the ground, they may appear simultaneous. To a passenger riding the train, however, the bolt toward the front may occur before the one at the back. Both views are correct within their own frames of reference. There is no single, universal now that applies to all observers. The present is no longer absolute. It depends on motion, and behind this dependence lies the constant speed of light. As the 20th century unfolded, the experimental confirmations piled up. Particle accelerators demonstrated time dilation directly. Cosmic rays showering Earth produced muons that lived longer than their normal lifetime because of their immense speeds. In 1971, the Haffel-Keating experiment flew atomic clocks on commercial airliners around the world. When compared with clocks left on the ground, the flying clocks had experienced time differently, exactly as relativity predicted. What had begun as a radical idea from a patent clerk had become one of the most verified theories in all of science. The consequences extended far beyond academic circles. The technology of modern life depends on relativity. Global Positioning System satellites orbit Earth with atomic clocks aboard. Because they move rapidly and are farther from Earth's gravity, their clocks tick at different rates compared with those on the ground. Engineers must correct for both special and general relativistic effects, or the system would drift, rendering navigation useless within hours. Every time a driver follows a map on their phone, They are unknowingly relying on Einstein's postulates and the constancy of C. In this way, relativity is not an abstract curiosity, but a daily companion. The constancy of light shapes not only the equations of physicists, but the routines of ordinary people. It determines how we measure, how we navigate, how we understand the flow of time itself. The world we inhabit, filled with satellites, accelerators, and digital networks, is bound together by the same principle Einstein embraced in 1905. And yet, even as relativity grew into one of the triumphs of human thought, the spirit of questioning remained. Could the speed of light truly be constant under all circumstances? Might it vary across the depths of cosmic history or in the intense environments near black holes? Einstein himself never treated his theories as the final word. He saw them as steps, provisional truths to be tested against the universe. The story of C was not finished. It had only entered a new chapter, one in which constancy was no longer a convenient assumption, but a law to be challenged by ever sharper experiments. As the echoes of Einstein's revolution spread through physics, one thing became clear: the speed of light was not merely a number. It was a principle, a boundary, and perhaps even the key to unifying the laws of nature. To question it was to question the very geometry of reality. To measure it was to measure the heartbeat of the cosmos itself, and to imagine it changing was to imagine the universe remaking its own rules. Thus, by embracing the constancy of light, Einstein had turned physics on its head. Space and time bent, energy and mass merged, and the universe revealed itself to be far stranger and more elegant than anyone had dared imagine. The next chapters in this story will show why constants matter, how they knit together the fabric of our equations, and what it would mean if even one of them, especially C, were ever to shift. In every equation of physics, in every attempt to capture the order of the universe in symbols, there appear numbers that seem to belong not to human invention, but to nature itself. These are the constants, the quantities that remain unchanged no matter where or when we measure them. They are not like the variables that dance across the chalkboard, shifting with conditions or initial states. They are the silent anchors, the deep pulses of the cosmos that set the rhythm for everything else. Without them, the equations would float, unmoored, unable to describe the world with any consistency. The speed of light, C, is perhaps the most famous of these, but it is not alone. Planck's constant, usually written as h, defines the graininess of the quantum world. It sets the scale at which particles cease to behave like tiny billiard balls and instead reveal their wave-like nature. The gravitational constant, G, tells us how strongly masses pull on one another across empty space, a number so small that it explains why we do not feel the tug of a nearby mountain, but why the Earth and Sun hold together in their great orbit. The Boltzmann constant, K, links temperature to energy, explaining why heat flows from hot to cold, and why the motion of molecules translates into the warmth we feel on our skin. Each constant serves as a bridge between human units and natural law. They allow us to turn the abstractions of equations into predictions about real particles, real forces, real measurements. Imagine trying to describe the orbit of a planet without the gravitational constant. The mathematics would collapse into symbols, with no scale, no way of telling whether the planet circled in seconds or in billions of years. Imagine trying to describe a photon without Planck's constant. Its energy would have no relation to its frequency, and the entire field of quantum mechanics would lose its anchor. Constants are what prevent physics from being a mere exercise in logic. They tie it to the real, measurable world. Among these, there is a special category, the dimensionless constants. These are pure numbers, stripped of units, the ratios that reveal the universe's inner harmonies. One of the most intriguing is the fine structure constant, usually denoted by the Greek letter alpha. It appears in the equations of electromagnetism, defined by the formula alpha equals E² divided by 4 pi epsilon 0 h bar c, where E is the charge of the electron. Epsilon 0 is the permittivity of free space. H bar is Planck's constant, divided by 2 pi, and c is the speed of light. When the numbers are put together, alpha turns out to be approximately 1 divided by 137. It is a pure ratio, a number with no units, and yet it governs the strength of electromagnetic interactions. The mystery of alpha has haunted physicists for decades. Why should it be this number and not another? Why should the universe have chosen 1 over 137 instead of 1 over 50 or 1 over 200? Richard Feynman once called it a magic number, written into the fabric of the cosmos with no explanation. Change alpha even slightly, and the chemistry of stars, the formation of atoms, the possibility of life itself, would be drastically altered. The fact that it contains within it c means that the speed of light is not just an isolated property, but part of a network of relationships that make the universe as its island. This is why constants matter. They are not arbitrary labels we assign. They are the conditions of existence. They determine whether atoms hold together or fly apart, whether gravity builds stars or fails to light the heavens, whether time flows smoothly or shatters into quantum uncertainty. They are not negotiable. They are the script of the universe itself, written in numbers that our equations only uncover. And yet the presence of these constants raises one of the deepest questions in physics. Why these numbers? Why this specific set, with their seemingly random values? Some, like the speed of light, can be defined by choice of units, fixed by how we measure time and length. But the dimensionless constants resist such tricks. They simply are what they are. Numbers that appear as if handed down without explanation. Some theories suggest they might emerge from deeper symmetries, hidden layers of physics we have not yet uncovered. Others suggest that perhaps they are environmental, set by the conditions of our particular universe, with other universes possessing different values. For now, the only certainty is that they are essential. To alter even one of them would unravel the equations that hold nature together. The delicate balance of constants is what allows stars to burn steadily for billions of years, what allows carbon to form in stellar furnaces, what allows life to arise on a small blue planet, circling an ordinary star. To contemplate constants is to realize how finely tuned the universe truly is, not in the sense of design, but in the sense of interdependence. They are the fabric, the scaffolding, the unyielding bones of reality. The presence of constants in our equations also serves as a reminder that physics is not merely about patterns we invent, but about structures that exist independently of us. The symbols we write on a board could be swapped for others. The units we use could be replaced by any convenient system, but the constants remain untouched. Whether we measure distance in meters or in miles, whether we count time in seconds or in heartbeats, the ratio between energy and mass, given by c², does not change. Whether we calculate atomic transitions in joules or in electron volts, the product of Planck's constant and frequency always gives the same result. Constants are not human conventions. They are the universe insisting on order. Think of music for a moment. A melody can be transposed into any key, yet the intervals between the notes remain fixed. It is the relationships that matter, not the arbitrary choice of starting pitch. In the same way, constants hold the relationships of nature steady, no matter what units we choose to describe them. They are the ratios, the hidden harmonies that make the cosmic music coherent. The fine structure constant is like a universal interval, a note ratio without which the harmony would collapse into noise. Some constants also define the boundaries of our knowledge. Planck's constant tells us where the quantum world begins, the point at which uncertainty becomes unavoidable, and particles refuse to behave like tiny stones. The gravitational constant tells us how the large-scale universe holds together, the measure of attraction that binds galaxies and shapes the curvature of space-time itself. The speed of light tells us how information can flow, the maximum pace at which cause can influence effect. Each constant marks a frontier, a line we cannot cross without leaving behind our current understanding. There is also something humbling about these numbers. They remind us that we are not free to build any universe we like. We live in one with specific rules, dictated not by choice, but by necessity. Had the constants been different, stars might never have formed. The chemistry of life might never have been possible. Even the stability of matter might have been compromised. The fact that we exist to ask these questions is itself testimony to the precise values of these constants. Some call this the anthropic principle, the observation that the universe must be compatible with our existence because we are here to observe it. Whether or not one embraces that reasoning, it is undeniable that the constants shape the conditions of everything we see. Einstein himself was deeply concerned with these numbers. He longed for a theory in which constants would not be arbitrary, but would fall naturally from deeper principles. He believed that the most beautiful laws of physics would be those in which the constants emerged inevitably, the way the circumference of a circle emerges from its diameter. To him, the true measure of success was not merely describing the universe as it is, but explaining why it could not be otherwise. That dream still drives modern physicists who search for unification, for a framework that might reveal why the values of the constants are what they are. Quantum field theory, string theory, and other attempts at unification all wrestle with this question. Some predict relationships between constants that might be tested in the future. Others hint that constants we now consider independent could one day be derived from a single underlying law. Yet so far, no theory has succeeded in explaining them all. We are left with a collection of numbers written into nature's code, waiting for a deeper key to unlock their necessity. And so we return to C, the most visible of them all. It is woven not only into relativity, but also into electromagnetism and quantum theory. It appears in the definition of alpha, binding together charge, Planck's constant, and the vacuum itself. To imagine C changing is not just to adjust one measurement, it is to alter the entire web of physics. The constants are not isolated pillars, but strands in a tightly woven net. Pull on one, and the rest shift. That is why they matter. That is why they must be tested again and again. In this way, constants act as both foundation and challenge. They give us stability, allowing predictions of extraordinary precision, but they also provoke us, demanding explanation. They ask us why these numbers are not others, why this delicate balance instead of another. They push us to dig deeper, to look beneath the equations for hidden symmetries, hidden truths. The constancy of C, the grain of H, the pull of G, the ratio of alpha, each is both an answer and a question, a door that opens onto deeper mysteries. To grasp how essential constants are, imagine stripping them away. Remove Planck's constant, and the quantum world collapses into classical predictability. A universe without uncertainty, without the dual nature of particles and waves, but also without the chemistry that depends on quantum bonds. Remove the gravitational constant, and there is no scale for attraction, no way to distinguish between the pull of a mountain and the pull of a star. Remove the speed of light, and relativity dissolves into contradictions, leaving no boundary between cause and effect. Without constants, physics is not merely incomplete. It is incoherent, like a story with its grammar erased. This is why constants often serve as the most direct probes of whether our theories are correct. If a constant were found to vary, even slightly, it would be a signal that something fundamental was missing from our understanding. Physicists build experiments around this idea, testing whether alpha is truly constant across billions of years, whether C has always been what it is now, whether G holds steady across the vastness of cosmic scales. Each test is both a confirmation of order and a challenge to discover cracks in that order. Consider how tightly these constants bind themselves into our everyday technology. The lasers that carry information through fiber optic cables depend on the frequency of light and its relation to energy through Planck's constant. The stability of matter that forms the silicon chips in computers relies on the electromagnetic strength governed by alpha. The satellites that orbit Earth and allow us to find our way on a map depend on relativity, and therefore on C. Without constants, there would be no measurements, no predictions, no technology, no science. Yet constants also remind us of the limits of our knowledge. Each time we measure them more precisely, we confirm their constancy within tighter margins. But what if they are not truly constant? What if they vary on scales too vast for our instruments, or in conditions too extreme for us to reproduce? The possibility keeps physicists vigilant. The constancy of constants is not assumed. It is always provisional, always open to revision in the face of evidence. There is also a deeper philosophical weight to them. The fact that the universe can be described by equations at all is astonishing. The fact that those equations contain constants, numbers that seem plucked from nowhere, is more astonishing still. Why should the universe be governed by mathematics at all? Why should numbers like 1 divided by 137 or 299,792,458 appear in its laws? These questions touch the border where science meets philosophy, where explanation meets wonder. For some, the existence of constants suggests that there may be deeper levels of reality still undiscovered. Perhaps they are residues of broken symmetries, fossils of a more unified era of the cosmos. Perhaps they are environmental, chosen randomly among many possibilities in a multiverse. Or perhaps they will one day be shown to follow inevitably from logic itself. For now, they remain as both answers and mysteries, guiding our search while refusing to yield their origins. As we close this chapter, the importance of constants should be clear. They are the scaffolding of physics, the hidden framework that supports every observation, every prediction, every technology. They matter because they are the difference between chaos and order, between equations that describe nothing and equations that capture the universe. And among them, the speed of light stands out, not just as a number, but as the heartbeat of relativity, electromagnetism, and quantum theory alike. The next step in our journey will show how far humanity has gone to test whether these constants truly deserve their name. Through experiments on Earth and observations across the cosmos, physicists have sought to confirm that C and its companions are unchanging. Precision has been the weapon, and nature has been challenged to reveal whether its anchors are indeed fixed. If constancy holds, our confidence in the laws of physics deepens. If it falters, new physics waits to be born. To declare something constant is one thing. To prove it, again and again, under every possible circumstance, is another. The history of physics is filled with confident declarations later overturned by sharper experiments. The Earth was once believed to be the center of the universe. Heat was once thought to flow like an invisible fluid. Atoms were once pictured as miniature solar systems with electrons orbiting like planets. Each idea fell when evidence proved otherwise. For this reason, when scientists call the speed of light a constant, they do so with both conviction and caution. Conviction, because every experiment so far has confirmed it. Caution, because history teaches that nature can always surprise us. The pursuit of testing C has therefore been relentless. In laboratories, on airplanes, in satellites, and in observatories gazing across billions of years, physicists have probed whether light's speed is truly immutable. Each test sharpens the definition of constancy, closing the window through which variation might slip. Each test is a conversation with the universe, asking, do you keep this promise everywhere, everywhere? On Earth, the most delicate tools are atomic clocks. These are not clocks in the ordinary sense, with ticking hands and swinging pendulums. They are devices that count the vibrations of atoms, such as cesium or strontium, whose natural oscillations are so regular that they can serve as the ultimate metronomes. An atomic clock does not merely measure time, it defines it. The second itself is defined by a certain number of cesium oscillations. When such clocks are compared across different conditions, moving, stationary, higher, lower, faster, slower, they become probes of relativity and of the constancy of C. In the 1970s, the Haffel-Keating experiment demonstrated this vividly. 4 cesium atomic clocks were flown around the world aboard commercial airliners, once eastward and once westward. When they returned, they were compared with clocks that had remained at the United States Naval Observatory. The results matched Einstein's predictions. The airborne clocks had shifted relative to the stationary ones, losing or gaining time depending on their direction of travel. The effect was tiny, measured in tens of nanoseconds, but it was real. It showed that time itself bent in response to motion, and that light's constancy was preserved by bending time rather than altering C. Other tests have pushed this further. Modern satellites carrying atomic clocks orbit Earth in conditions where both velocity and gravity affect their passage of time. Engineers who built the Global Positioning System quickly discovered that without corrections for relativity, their satellites would drift by kilometers each day. The system works precisely because C is constant, and because relativity accounts for how time and distance adjust around it. Every time someone checks a location on a phone, they are unwittingly verifying the constancy of light. Laboratory interferometers have also played a crucial role. These instruments split beams of light and send them along different paths before recombining them. If the speed of light varied depending on direction, as once expected in an ether, the recombined beams would produce shifting patterns. But they do not. Even with modern interferometers of extraordinary sensitivity, no such variation has been found. These devices can detect differences smaller than the width of a single atom, yet C has remained constant to within their limits. Particle accelerators provide another stage for testing. When particles approach near light speeds, their behavior depends critically on the value of C. If the speed of light varied even slightly, the enormous machines built to hurl particles around rings and smash them together would reveal the discrepancy. Instead, the accelerators confirm the predictions of relativity with exquisite precision. Muons live longer at high speeds, exactly as expected. Energies and momenta balance, as they should. Light, in all its stubborn constancy, continues to rule, and yet, no experiment is ever the final word. Each test tightens the leash, but never removes the possibility that a deeper truth lies hidden. Scientists measure again and again, not because they expect to find C wavering on a casual Tuesday afternoon, but because testing is the essence of science. To assume constancy without checking would be to abandon the discipline itself. By measuring, they transform belief into knowledge, provisional yet ever stronger. The search for constancy has never been confined to Earth alone. Our planet provides an excellent laboratory, but it is still a limited corner of the cosmos. To test whether the speed of light truly holds everywhere, scientists have turned to the skies. One of the first natural experiments was written into the heavens themselves. Every time a star's light passes near the limb of the sun, its path bends, not because C changes, but because gravity curves the space through which it travels. This bending, confirmed during eclipses beginning in 1919, is itself a testimony to constancy. Rather than altering the speed of light, the universe preserves it by altering the geometry around it. Satellites carry the pursuit further. Orbiting hundreds of kilometers above Earth, they allow comparisons of atomic clocks in different gravitational environments. General relativity predicts that clocks run faster at higher altitudes because gravity is weaker. Experiments confirm this, with differences measurable in billionths of a second. Yet the speed of light remains untouched, held constant, while time itself stretches and contracts to obey it. This balancing act is one of the great marvels of relativity. Nature does not allow C to change. Instead, it bends time and space themselves so that C remains inviolate. Some of the boldest tests have involved sending clocks on journeys through space. Spacecraft like Galileo, Cassini, and others carried radio transmitters whose signals were tracked with extraordinary precision as they moved across the solar system. Any deviation in the way those signals traveled would have betrayed a change in C. None was found. Light continued to behave exactly as predicted, crossing millions of kilometers with unwavering fidelity. High-energy physics has provided even stranger episodes. In 2011, the Opera collaboration in Italy announced that they had measured neutrinos traveling faster than light. For a moment, the world reeled. Headlines declared Einstein wrong, and speculation ran wild. If true, the finding would have overturned a century of physics. But science demands patience. Other teams checked, and Opera themselves dug deeper. In the end, the anomaly was traced to a loose cable and a miscalibrated clock. The universe had not betrayed relativity after all. C remained constant, and the episode became a reminder of why extraordinary claims demand extraordinary evidence. The discipline of precision has grown ever more exacting. Today, laboratory experiments probe the constancy of C to astonishing levels, finding no variation to within parts in 100 trillion. This is like measuring the distance from Earth to the nearest star and finding the error no larger than the width of a human hair. Such is the rigor with which constancy is tested. Yet physicists are not satisfied with present accuracy alone. They push further, designing new generations of optical clocks based on strontium or ytterbium atoms, whose ticks are more stable than any heartbeat, any pendulum, any crystal oscillator ever built. These clocks, operating with lasers cooled to near absolute zero, are capable of detecting differences in time flow between two heights, separated by only a few centimeters. With such devices, scientists can probe relativity on the scale of a tabletop, confirming again that light's constancy is preserved even in the tiniest variations of gravitational potential. The very existence of such experiments illustrates the spirit of physics. Constancy is never assumed simply because it seems convenient. It is always measured, always challenged, always confronted by sharper tools. And so far, light has met every challenge. Whether bouncing between mirrors in a laboratory, racing alongside satellites, or spanning the void between planets, C has shown no sign of wavering. Still, the story is not complete. Earth and its orbit provide only a narrow range of conditions. To probe whether constancy has held since the birth of the cosmos, scientists must look further. They must turn their eyes to the ancient light of the universe itself, light that has traveled for billions of years, carrying with it the memory of early epochs. In those distant photons lies the chance to ask whether C has been constant not only here and now, but across all of cosmic history. The idea of constancy is never fully settled until it is tested against the broadest canvas available. And for physicists, that canvas is the universe itself. Light that reaches us from distant galaxies began its journey billions of years ago, long before Earth existed. As it crosses the void, it carries with it the imprint of physical laws, as they were when it first set out. If the speed of light had changed during that immense span of time, the evidence would be written in those ancient beams. To look at the cosmos is to peer into a vast archive of experiments already performed by nature. One of the richest sources of evidence comes from pulsars, rapidly rotating neutron stars that sweep beams of radiation across space, like cosmic lighthouses. Their pulses arrive with astonishing regularity, so precise that they rival atomic clocks. Any change in the speed of light along their journey would distort the timing of these pulses. Observations spanning decades reveal no such distortion. The pulses arrive exactly as expected, confirming that C has remained constant across immense distances and times. Another test comes from gamma-ray bursts, titanic explosions in distant galaxies that release more energy in seconds than our sun will emit in its entire lifetime. These bursts send out photons across a vast range of energies. If the speed of light depended on energy, higher energy photons would arrive at different times than lower energy ones, after traveling billions of years. Yet detectors on Earth, including those aboard satellites, show that they arrive nearly simultaneously. The margin of difference is so tiny that it places strict limits on any possible variation in C. Even more dramatic confirmation came in 2017, when gravitational waves were detected from the collision of two neutron stars. Just seconds later, gamma rays from the same event arrived at Earth. The waves and the light had traveled for over 100 million years across the cosmos. Their near-simultaneous arrival showed that gravity and light move at the same speed, to within 1 part in 100 quintillion. This is one of the most precise confirmations of constancy ever achieved, demonstrating that even across cosmic baselines, C remains unshaken. These astronomical tests complement the laboratory measurements on Earth, forming a web of evidence that stretches from the smallest scales to the largest. Each test closes the gap through which variation might hide. Together they paint a picture of extraordinary stability. Light moves as it always has, at the same pace, regardless of energy, direction, or epoch. And yet, scientists do not stop. The search for possible variation continues, not because they expect to find it, but because science thrives on doubt. Future telescopes will probe the earliest galaxies, measuring whether the fingerprints of atomic transitions reveal any subtle drift in constants. Future gravitational wave detectors will stretch their reach deeper into the cosmos, tightening the leash on possible deviations. With each step, the universe is asked again, is C truly immutable? The answer so far has been yes, within margins that grow ever smaller. But the very act of questioning remains vital. If one day evidence revealed even the faintest crack, it would open the door to new physics, perhaps even to a deeper unification of forces. If instead, constancy continues to hold, then confidence in our current framework will grow stronger still. In both outcomes, science advances, guided not by certainty, but by curiosity. The precision tests of C remind us of the delicate dance between belief and evidence. To call light speed a constant is not an act of faith, but of persistence, of measuring again and again until the universe itself speaks. So far, the verdict is clear. Light remains unyielding, its pace the same across laboratories, satellites, galaxies, and epochs. The constancy of C has survived every challenge. But in science, survival today only sets the stage for the next trial tomorrow. As we leave the realm of laboratory precision and enter the vast expanse of cosmology, the questions deepen. Has C always been constant, even in the newborn universe? Could the earliest moments of time, when the cosmos was a dense and fiery sea of particles, have allowed light to behave differently? To explore this, we must turn to the story of the universe itself, where horizons and origins test the very limits of our understanding. The constancy of light does not belong only to laboratories and satellites. It stretches back into the earliest moments of cosmic history, when the universe itself was young and turbulent. To ask whether C has always been the same is to ask whether the very foundations of reality were fixed at the birth of time, or whether they have shifted as the cosmos has aged. The story of light is therefore also the story of cosmology, the science that seeks to understand the universe as a whole. In the framework of general relativity, the speed of light is more than a number. It is woven into the very geometry of space-time. Einstein's field equations, which describe how matter and energy curve space and how that curvature dictates motion, are built around C. It appears not only as the maximum speed at which information can travel, but also as the conversion factor that links space and time into a single fabric. Remove or alter it, and the equations lose their coherence. When we trace the universe backward through time, guided by these equations, we arrive at the hot, dense state we call the Big Bang. In those first moments, the cosmos was filled with searing radiation and particles colliding at energies beyond anything we can reproduce on Earth. Light in that furnace was trapped, scattering endlessly among charged particles, Only hundreds of thousands of years later, when atoms first formed and the universe cooled, did light escape to travel freely. That light became the cosmic microwave background, a relic still visible today. But before we reach that stage, we encounter a puzzle that forces us to think carefully about the role of C. This is the horizon problem. When we look at the cosmic microwave background, we see that it is astonishingly uniform. Regions of the sky separated by billions of light years have nearly the same temperature, as though they had somehow been in contact to share information. Yet according to relativity, light could not have traveled far enough in the early universe for those regions to exchange signals. They should not look the same, and yet they do. The leading explanation for this puzzle is inflation, a period of extremely rapid expansion that stretched space by unimaginable factors in a fraction of a second. In this view, regions that were once in close contact were blown apart, preserving their uniform conditions across vast distances. Inflation solves not only the horizon problem, but also other puzzles, such as why the universe appears flat on large scales. It is a powerful idea, supported by much evidence, though it remains a theory awaiting full confirmation. Yet inflation is not the only possible answer. In the 1990s, some physicists proposed that perhaps the speed of light itself was not constant in the early universe. If C had been larger in the past, then light could have traveled farther, linking regions that today seem causally disconnected. This class of ideas became known as variable speed of light theories, or VSL for short. Proposed by thinkers like Jaume Gayjo and Andreas Albrecht, these models challenged the assumption of constancy at the most fundamental level. The boldness of VSL lies not just in suggesting that C could change, but in using that change to solve real cosmological problems. If light were faster in the early universe, the horizon problem would vanish, for distant regions would have been in causal contact. The smoothness of the cosmic microwave background would then follow naturally. In this way, a variation in C becomes an alternative to inflation, a rival attempt to explain the universe's earliest conditions. These theories are controversial. They raise difficult questions about how to formulate laws of physics consistently if a constant like C is allowed to vary. They must be constructed carefully to avoid contradictions, for much of modern physics rests on the assumption that C is fixed. Yet they are not mere speculation. They are published, debated, and tested within the scientific community, part of the ongoing effort to explore every possible path to truth. What is striking is that the constancy of light, so firmly established in every experiment we can perform today, becomes a point of debate when we extend our gaze to the dawn of time. The very fact that scientists consider such radical ideas shows the humility of the discipline. No constant is above questioning, not even the one upon which so much of physics is built. To test whether C has always been the same, we must turn to the universe itself, to its oldest light and deepest structures. Only there can we ask whether the laws we see today were already written in the first flicker of creation. The proposal of inflation changed cosmology forever. When it was first introduced in the early 1980s by Alan Guth and later refined by Andre Linde and others, it seemed almost too bold to believe. It claimed that in less than a trillionth of a second, the universe expanded by a factor so enormous that distances, once smaller than an atom, were stretched to scales larger than galaxies. This burst of expansion smoothed out irregularities, flattened space, and explained the remarkable uniformity we see in the cosmic microwave background. It was an elegant solution, and over the decades, observations of the sky have continued to support its predictions. Yet as powerful as inflation is, it is not without its mysteries. What mechanism drove it? What field of energy fueled that expansion? How did inflation end, leaving behind the hot Big Bang we can describe with confidence? These are questions still without complete answers. And whenever a theory leaves gaps, scientists are compelled to ask whether alternatives exist. Variable speed of light theories arose in that spirit, not as a dismissal of inflation, but as a challenge, a way of probing whether another road might lead to the same destination. In a VSL scenario, the universe does not need to inflate at extraordinary rates. Instead, the speed of light itself was much greater in the earliest moments. With a higher c, photons could travel vast distances, bringing distant regions into causal contact before the cosmos cooled. Uniformity, instead of being stretched across the sky by inflation, was carried there by light itself. In principle, this could explain the smoothness of the microwave background without invoking an inflaton field or a sudden burst of expansion. But this raises deep questions. If c could vary, what would that mean for the equations of physics? Relativity depends on the invariance of light's speed. If that invariance fails, then the very geometry of space-time would need to be rewritten. The principle of relativity, which underpins not only Einstein's work, but all of modern physics, would be upended. For this reason, VSL theories are delicate, requiring careful mathematical frameworks to remain consistent. They are not simply a matter of changing a number. They demand a reconstruction of the laws themselves. Supporters of VSL argue that the challenge is worth facing. After all, physics has seen revolutions before. Newton's laws gave way to relativity and quantum mechanics. Certainties once held unshakable have dissolved when new evidence demanded it. Why should the constancy of c be immune? If varying c provides a simpler explanation for early universe puzzles than inflation, it deserves consideration. Critics reply that inflation already explains much, that it has been tested against detailed observations of the microwave background, and that VSL must clear an equally high bar of evidence. The debate between these ideas illustrates the dynamic nature of science. It is not a matter of faith in one theory or another, but of weighing which better matches the evidence. Inflation, with its predictions of subtle patterns in the microwave background, has so far matched observations with impressive accuracy. VSL remains speculative, lacking the same breadth of predictive success. Yet the fact that it is even on the table reminds us that no constant, not even the speed of light, is above scrutiny. In cosmology, the stakes of these debates are immense. To say that c has always been the same is to claim that the rules we measure in laboratories today were already fixed in the fiery chaos of the first fraction of a second. To say that it may have varied is to claim that the universe itself has evolved not only in content but in its most fundamental laws. Either answer changes how we understand our place in the cosmos. The conversation continues in conferences, in journals, in the quiet work of theorists and observers. Inflation remains the leading explanation, but VSL keeps alive the spirit of questioning. For every elegant theory, there is a shadow of doubt, and in that shadow lies the potential for discovery. The early universe, with its mysteries of horizons and uniformity, demands that we ask these difficult questions. And in asking them, we keep alive the most important constant of all, the refusal to accept without testing. To appreciate the stakes of these questions, it helps to remember that cosmology is not merely the study of distant galaxies, but the attempt to trace every atom of our own existence back to its origin. When we ask whether the speed of light has always been constant, we are asking whether the very fabric of time that carries our lives forward was already fixed when the universe was no more than a hot blur of particles. If c has been steady since the beginning, then the laws we measure today are truly ancient, older than stars, older than atoms. If it has not, then the rules of reality have shifted, and our present universe is only one chapter in a story whose laws have evolved. The evidence so far leans toward constancy. Observations of the cosmic microwave background reveal a uniformity and a set of acoustic patterns that inflation predicts with uncanny precision. The minute fluctuations measured by satellites like WMAP and Planck match the models of an inflating universe more closely than any alternative has managed. These measurements do not directly rule out VSL, but they give inflation a strong foothold. In science, the theory that explains more with fewer assumptions holds the advantage. And for now, inflation wears that crown. Still, the allure of VSL lingers. It offers a vision in which light itself plays an even deeper role, not just as the messenger of information, but as the agent that shapes cosmic history. To imagine C as variable is to imagine a universe less rigid, more dynamic, in which the most fundamental constants evolve, along with the cosmos they govern. Such ideas resonate with the philosophical desire to see the universe not as a fixed machine, but as a living, changing reality. Whether inflation or VSL, or some as yet unimagined theory ultimately proves correct, what matters is the process by which these questions are pursued. Cosmologists do not rest content with elegant mathematics. They look to the sky, to the faint glow of the microwave background, to the arrangement of galaxies, to the traces of gravitational waves. They measure, they compare, they test. Theories rise and fall, not by beauty alone, but by contact with the universe itself. The early universe remains one of the greatest laboratories for these tests. In those first instants, when energy densities were unimaginably high, the laws of physics may have operated differently from how they do now. Our task is to read the evidence left behind, to reconstruct what happened in an epoch we can never visit, but only infer. Whether the speed of light was already fixed, or whether it changed, is part of that reconstruction. The answer lies in the faint signals we still receive from those times, written in photons, that began their journey billions of years ago. There is a lesson here beyond the technical debates of cosmology. It is the lesson that even the most fundamental assumptions of science must remain open. To call something constant is not to declare it beyond question, but to declare it a hypothesis, tested and confirmed so far, but always provisional. The moment science ceases to test its constants is the moment it ceases to be science. That is why cosmologists examine the microwave background, why they debate inflation and VSL, why they build ever more precise telescopes. The goal is not to prove themselves right, but to give the universe the chance to prove them wrong. As we close this chapter, we stand at the threshold between what we know and what we seek. The constancy of light has been confirmed in every experiment on Earth, and inflation explains the great puzzles of cosmic uniformity. Yet the possibility remains that one day, evidence may point to a deeper truth, perhaps even a universe in which C itself has a history. Whether or not that day comes, the search will continue. For in questioning the constancy of light, we are not merely testing a number, we are testing the very faith we place in the permanence of natural law. The next step in our journey will carry us to the light itself, to the ancient photons still streaming across the sky from the time when the universe was less than 1 million years old. This glow, the cosmic microwave background, is the most perfect laboratory we have for probing the constancy of C in the early universe. It is a whisper from creation, and within it may lie the answers to whether light has always kept the same pace, or whether it once raced differently across the newborn cosmos. If the early universe was a furnace, then the cosmic microwave background is the afterglow of its fire. It is the oldest light we can see, released when the cosmos was young, only about 380,000 years old. Before that moment, the universe was opaque. Photons collided constantly with free electrons, unable to travel far before being scattered. Space was filled with a fog of light, dense and blinding. But as the universe expanded and cooled, atoms formed, trapping electrons in orbits around nuclei. The fog lifted. Photons were freed to stream through space, carrying with them a snapshot of the conditions at that time. Those same photons, stretched by the expansion of space into microwave wavelengths, still arrive at Earth today. They fill the sky in every direction, a faint glow, invisible to our eyes, but detectable by sensitive instruments. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the cosmic microwave background, or CMB, soon became one of the cornerstones of modern cosmology. What began as a puzzling hiss in a radio antenna was quickly recognized as the very echo of the Big Bang. It was the strongest confirmation yet that the universe had begun in a hot, dense state and had been expanding and cooling ever since. The CMB is more than just evidence of the Big Bang. It is a map, a record of the universe's infancy, written in light. Over the decades, satellites have charted this glow in increasing detail. The COBE satellite in the early 1990s measured the spectrum of the CMB and showed it was a near-perfect blackbody, just what theory predicted. COBE also detected tiny fluctuations, differences in temperature only a few parts in 100,000, scattered across the sky. These small irregularities, faint ripples in the otherwise uniform glow, were the seeds of galaxies, the tiny variations in density that gravity would later amplify into stars, clusters, and vast cosmic structures. Later missions, WMAP in the 2000s and Planck in the 2010s, sharpened this picture with breathtaking precision. They mapped the entire sky, charting the minute anisotropies of the CMB with resolution high enough to test theories of the early universe. From these measurements, cosmologists have learned not only the age and composition of the cosmos, but also the geometry of space itself. The CMB reveals that the universe is astonishingly flat on large scales, just as inflation predicts. But beyond confirming inflation, the CMB also provides a unique laboratory for testing whether the speed of light has always been constant. If C were different in the early universe, it would have changed how photons and matter interacted, altering the patterns we see today. The ripples in the CMB would bear the signature of that change. The peaks and troughs in its power spectrum, the acoustic oscillations of primordial plasma, are exquisitely sensitive to the value of C. In this way, the microwave background is not only a relic of the past, but a tool for probing the constancy of the laws of physics themselves. The remarkable uniformity of the CMB poses the horizon problem that inflation was designed to solve, but it also sets strict limits on any theory that suggests C may have varied. The smoothness across the sky, combined with the precise spectrum of fluctuations, constrains just how much change could ever have occurred. While VSL theories offer an alternative solution, the CMB makes clear that if the speed of light was different, it could not have been radically so. The patterns in the microwave glow leave little room for wild variation. In this way, the CMB acts as a cosmic referee. It carries the fingerprints of the early universe and enforces the rules of physics across billions of years. To measure it is to ask the universe directly whether light has always kept the same pace. So far, the answer has been yes, within the astonishing precision of our instruments. But as always, the search continues, for the faintest whisper of deviation might still hide in those ancient photons. The ripples frozen into the cosmic microwave background are more than random noise. They are the echoes of sound waves that once pulsed through the primordial plasma of the early universe. Before atoms formed, the cosmos was filled with a dense mixture of photons, electrons, and protons, locked together in a hot fluid. In that sea, pressure and gravity competed, producing oscillations much like the compressions and rarefactions of sound traveling through air. These oscillations left their imprint on the photons that were released when the universe became transparent. Today, we see them as a series of peaks and troughs in the angular power spectrum of the CMB, a pattern that reveals how matter and light were intertwined. The position of these peaks is sensitive to the speed of light. If C had been different, the waves would have propagated at a different pace, shifting the characteristic scales imprinted in the microwave sky. The fact that the observed peaks match the predictions of standard cosmology so precisely is one of the strongest confirmations that C has remained unchanged since those earliest times. The photons themselves carry the record, a kind of fossilized testimony of the laws under which they once moved. The polarization of the CMB provides another layer of evidence. As photons scattered off electrons in the early plasma, they picked up subtle directional preferences, producing patterns of polarization across the sky. These patterns, mapped with increasing accuracy by missions like Planck, contain additional information about the geometry and evolution of the universe. Once again, the predictions align beautifully with the assumption that c has been constant. A varying speed of light would scramble these delicate alignments, leaving signatures that we simply do not see. This is not to say that cosmologists have stopped looking. On the contrary, every refinement in measurement is also a new test. Future missions, both satellites and ground-based observatories, aim to probe the CMB with even greater sensitivity. They will search for faint traces of primordial gravitational waves, for subtle distortions in the spectrum, for any hint of new physics that might lurk beyond the standard model of cosmology. Each new dataset will also serve as another interrogation of c, asking whether the universe has kept faith with its constancy since the beginning. It is remarkable that such profound questions can be asked by examining light that has been traveling for nearly 14 billion years. Each photon of the CMB has crossed the expanding universe, redshifted from searing heat into gentle microwaves. Along the way, it has passed galaxies, clusters, and voids, carrying with it a memory of its origin. That we can capture these photons with instruments on Earth and in orbit, and decode their message with equations, is one of the triumphs of modern science. The CMB has taught us that the universe is old, about 13.8 billion years. It has shown us that only about 5% of the cosmos is made of ordinary matter, while the rest is dark matter and dark energy. It has confirmed that space is nearly flat, and that the seeds of galaxies were quantum fluctuations magnified to cosmic scales. And woven through all these discoveries is the silent affirmation of c, the speed that connects time and space, still holding steady after billions of years. Yet the value of the CMB is not only in what it confirms, but in what it allows us to question. For those who pursue VSL theories, the microwave background is both obstacle and opportunity. Any viable model must reproduce its precise patterns, must show how a changing speed of light could still produce the sky we see. This is a high bar, and most variations have struggled to clear it. But science progresses by such struggles. By testing alternatives against the CMB, we do not weaken our confidence in constancy. We strengthen it, because only what survives such scrutiny can claim to be true. The CMB is therefore both relic and laboratory, a message from the past, and a tool for the present. It does not merely remind us of where we came from. It allows us to test the laws that govern our reality, to ask whether they have always been what they are now. And so far, those ancient photons have spoken with one voice. Light has never strayed from its pace. The cosmic microwave background is often described as the baby picture of the universe, but it is also something more subtle and powerful. It is the closest thing we have to a controlled experiment on a cosmic scale. Every photon that makes up this glow was released under the same conditions, at the same moment, and has traveled to us across the expanding universe. Unlike the light of stars, which carries the complexities of nuclear fusion and stellar atmospheres, the CMB carries the imprint of primordial physics, almost untouched. It is a pristine signal, a baseline against which all theories must be measured. One of the striking features of the CMB is its astonishing uniformity. Across the entire sky, the temperature is nearly the same, to within 1 part in 100,000. If C had been different in those early moments, that uniformity would look different. Some regions would be warmer, others cooler, the imprint of light having traveled at different rates. Instead, the near-perfect uniformity reinforces the idea that the laws we know today were already in place when the universe was only a few 100,000 years old. But hidden within that uniformity are tiny irregularities, the seeds of structure. These are not flaws but treasures, the subtle variations that gravity would later amplify into galaxies and clusters. The exact size and distribution of these ripples depend on how light and matter interacted in the early plasma. The fact that our models, built on the assumption of a constant c, reproduce these patterns so accurately is one of the most powerful arguments for constancy. If light had traveled at any other speed, the map of the sky would not match what we observe. Still, cosmologists keep searching for ways in which the CMB might reveal surprises. They analyze not only the temperature fluctuations but also the polarization patterns, looking for the faint signatures of primordial gravitational waves. They study distortions caused by intervening clusters of galaxies, using the CMB as a backlight to probe cosmic structure. They compare measurements from different instruments to rule out systematic errors. In all these efforts, the constancy of light is a silent assumption, tested with every new refinement. It is a profound thought that the photons now captured by our detectors began their journey before there were stars, before there were planets, before there was even the possibility of life. For nearly 14 billion years, they have been traveling at sea, never wavering, never slowing, never hastening. That unwavering pace is itself the evidence of constancy. Each photon is a witness, carrying the testimony of its journey. Together, they form a chorus that sings of laws unbroken. The story of the CMB also reveals something about the nature of science itself. It shows how patient measurement, combined with bold theory, can turn the faintest signals into profound truths. From a hiss in an antenna to a detailed map of the cosmos, the CMB has transformed our understanding of the universe. It has revealed the age, composition, and geometry of everything we see. And it has given us one of the clearest answers yet to the question of whether light has always been constant. The answer is not an absolute yes, because science never deals in absolutes. It is a provisional yes, tested to the limits of our instruments, always open to revision if new evidence appears. That is the strength of the scientific method. It does not freeze truth, but allows it to evolve. The constancy of light has survived every test so far, and the CMB is its most eloquent witness. But the search continues, because to stop searching would be to betray the very curiosity that led us here. As we leave the story of the microwave background, we turn to another approach for testing constancy. Instead of looking at the relic glow of the early universe, we look at the light of quasars, the brilliant beacons powered by supermassive black holes in the distant cosmos. Their spectra, stretched across billions of years, allow us to probe whether the fine structure constant, and with it the speed of light, has shifted over time. The CMB has spoken of constancy in the young universe. Quasars may tell us whether that constancy has held across the eons since. Among all the constants of nature, few carry as much mystery as the fine structure constant, often denoted by the Greek letter alpha. Unlike the speed of light, which is tied to our units of length and time, alpha is a pure number. It is dimensionless, stripped of any human convention. Its value is about 1 divided by 137, a ratio that seems almost magical in its precision. It governs the strength of electromagnetic interactions, deciding how electrons orbit nuclei, how atoms absorb and emit light, how chemistry unfolds, and ultimately, how the universe organizes itself into stars and life. The fine structure constant is defined by a formula that weaves together several of the most fundamental quantities in physics. It is equal to the square of the electron's charge, divided by 4 pi, times the permittivity of free space, multiplied by Planck's constant, divided by 2 pi, and by the speed of light. In other words, alpha is not an isolated number. It is a nexus, a meeting point, where charge, quantum action, the vacuum, and C all converge. Any variation in C would ripple into alpha, altering the fabric of atomic structure itself. If alpha were even slightly different, the world would not be the same. A larger alpha would mean stronger electromagnetic forces, electrons bound more tightly to nuclei, chemistry altered beyond recognition. A smaller alpha would loosen those bonds, destabilizing atoms and undermining the processes that build life's complexity. In either case, stars might burn too quickly or fail to fuse elements, and carbon, the element at the heart of life, might never form. That is why physicists treat alpha as one of the most precious numbers in nature, a number that seems almost tuned to allow our existence. But the question remains, has alpha always been the same? If it has changed across billions of years, then the speed of light, or some other fundamental quantity in its definition, must have changed as well. To test this, scientists look far into the universe, using quasars as their probes. Quasars are the blazing cores of young galaxies, powered by supermassive black holes consuming matter at furious rates. Their light travels to us across billions of years, carrying with it absorption fingerprints imprinted by clouds of gas along the way. These fingerprints, seen as spectral lines, are exquisitely sensitive to the value of alpha. If alpha were different when that light was absorbed, the positions of the lines would shift ever so slightly. Astronomers collect the spectra of distant quasars using powerful telescopes, spreading the light into rainbows and examining the fine details of absorption. Each line corresponds to a specific transition in atoms, usually hydrogen, or heavier elements like magnesium or iron. The precise spacing of these lines depends on alpha. By comparing the observed spectra with laboratory measurements on Earth, scientists can test whether alpha has remained unchanged across billions of years. The task is daunting. The shifts they seek are minuscule, far smaller than a single pixel in a detector. They must account for motions of galaxies, distortions of instruments, and the gravitational redshift of light climbing out of deep wells. Yet the reward is great, for even the faintest sign of variation would revolutionize physics. It would mean that the constants we treat as absolute are instead part of a deeper, evolving story. In the late 1990s and early 2000s, a team led by John Webb reported tantalizing hints that alpha might not be constant. Using data from the Keck Observatory in Hawaii, they suggested that the fine structure constant was slightly smaller billions of years ago, by a few parts in 100,000. The result was controversial, sparking both excitement and skepticism. If true, it would mean that C or other constants had shifted, rewriting the history of physics. Other groups tried to replicate the finding with different telescopes and methods. Some confirmed the hint, while others found no variation at all. The debate continues, sharpened by improvements in instrumentation. The European Southern Observatory's Very Large Telescope in Chile has provided data of extraordinary quality, yet the results remain mixed. Some analyses suggest small variations, others rule them out. The question of whether alpha has changed remains open, balance between possibility and constancy. The controversy surrounding the fine structure constant is a reminder of how fragile the search for variation can be. To detect a change of only a few parts in 100,000 across billions of years requires instruments of almost unimaginable precision. A single shift in the calibration of a spectrograph, a subtle drift in the way light is recorded by a detector, or even a change in the atmosphere above the telescope can mimic the effect of a varying alpha. For this reason, every claim must be weighed against the possibility of systematic error. When Webb and his colleagues announced their results, the physics community responded with a mixture of curiosity and caution. The idea that a constant could vary was breathtaking, but the potential for error was immense. Other groups reanalyzed the same data, applying different corrections. Some found support for variation, others did not. Observations from the Keck Observatory and the Very Large Telescope seem to tell slightly different stories. Keck's data hinted at a smaller alpha in the distant past, while the VLT's data suggested no change. Still others found a curious pattern, as if alpha might vary across the sky, being slightly larger in one direction and slightly smaller in another. Such a cosmic dipole, if real, would be revolutionary, but it remains far from confirmed. The difficulty lies in separating the signal from the noise. When light from a quasar passes through a gas cloud billions of light years away, it encounters atoms that imprint absorption lines on its spectrum. Those lines shift not only with alpha, but also with the velocity of the cloud, with local conditions, with gravitational fields. Instruments must be calibrated to account for every effect, down to the smallest distortion. Even the way starlight bends through Earth's atmosphere can introduce subtle errors. In such a delicate arena, certainty is elusive. Despite these challenges, the effort continues. Astronomers refine their techniques, developing spectrographs designed with stability in mind, locked against thermal expansion, vibration, or any source of drift. One of the most advanced is ESPRESSO, mounted on the Very Large Telescope in Chile. It is capable of measuring shifts in spectral lines with precision that was once unimaginable. With such tools, scientists hope to settle the question of whether alpha is truly constant, once and for all. The implications of variation would be staggering. If alpha has changed, then either the electron's charge, Planck's constant, or the speed of light must have changed. Each possibility would shake the foundations of physics. A varying alpha would ripple through quantum mechanics, electromagnetism, and relativity, demanding a new framework to explain why and how constants evolve. It would point to physics beyond the standard model, perhaps linked to extra dimensions, scalar fields, or other exotic ideas at the frontier of theory. For now, the evidence is inconclusive. The most careful studies find no change, while a few still suggest subtle variation. The disagreement is not failure, it is science in action. Every telescope that gathers quasar light adds another piece to the puzzle. Every new instrument refines the limits, tightening the leash on what variation could exist. Even a null result, the confirmation that alpha has not changed, is profound, for it deepens our confidence that the laws we know are as ancient as the universe itself. It is worth remembering that the mere act of questioning alpha's constancy reflects the spirit of physics. Constants are not worshipped as eternal truths, but treated as hypotheses, always open to challenge. The search for variation is not a sign of doubt in science, but of its strength, for only a discipline, unafraid of being wrong, can hope to be right. Whether alpha has changed or not, the effort to find out drives progress, sharpening instruments, refining theories, and deepening our connection to the cosmos. The fine structure constant is thus both a mystery and a compass. It points us toward the deepest questions. Why is the universe built the way it is, and could it have been otherwise? By studying quasars and their ancient light, we are not only probing alpha, but also exploring the possibility that the laws of nature themselves may be dynamic, shifting with time and space. If they are, then the story of the universe is richer than we have ever imagined. If they are not, then the constancy itself is a truth as profound as any change could be. The search for variation in the fine structure constant is as much about philosophy as it is about physics. On one level, it is a technical question, pursued with spectrographs and quasar light, answered with error bars and statistical analysis. But on another level, it touches the deepest assumptions we make about reality. To imagine that a constant might change is to imagine that the rules of the universe are not fixed but evolving, that what we call laws are more like chapters in a longer story. It is a thought that unsettles and inspires in equal measure. When we look at the night sky, we are seeing across time. Light from distant quasars began its journey billions of years ago, when Earth was young or had not yet formed. By comparing that ancient light with the light of today, we are comparing the laws of physics across epochs. So far, the evidence suggests that alpha has held steady, but the mere possibility of difference has opened doors in theory. Some models of the universe propose that constants may be tied to hidden fields that can evolve over time. Others suggest that if there are multiple universes, each may have its own set of constants, with ours being simply one realization among many. In such views, alpha is not uniquely privileged. It is a roll of cosmic dice that happen to yield a number, allowing stars and life. If one day a variation is confirmed, it would not only reshape physics but also philosophy. It would force us to reconsider what we mean by law. Are the laws of nature eternal, carved into the structure of reality? Or are they provisional, shaped by deeper processes we do not yet understand? The history of science suggests the latter, that what we call constants may be only approximations to truths still hidden. Each discovery, from relativity to quantum mechanics, has shown that yesterday's absolutes can become today's approximations. Alpha may yet follow the same path. For now, the balance tilts toward constancy. The most sensitive instruments tell us that if alpha has varied at all, the change is smaller than 1 part in a million over billions of years. That stability is extraordinary. It means that the chemistry of stars, the structure of atoms, and the processes of life have unfolded under the same rules for nearly the entire age of the universe. The cosmos, vast and evolving, has kept its constant steady, at least within the precision we can measure. And yet, the story is unfinished. New instruments are coming online, more stable and more accurate than ever before. Espresso in Chile hires planned for the next generation of telescopes, and future space-based missions will probe Alpha with precision unimaginable just a decade ago. Each will extend our reach, looking deeper into time and further across space. Perhaps they will confirm constancy beyond doubt. Perhaps they will find a crack in the facade, a hint that change lurks in the margins. Either outcome will enrich our understanding, for science does not advance by answers alone, but by the questions that drive them. The search for variations in the fine structure constant is thus not a distraction from physics but its essence. It embodies the refusal to assume, the insistence on testing, the humility to let nature speak for itself. Whether alpha is fixed or shifting, the act of asking is what matters most. For in asking, we remind ourselves that even the deepest truths we know are only provisional, waiting to be confirmed by the universe itself. As we close this chapter, we move from the light of quasars to the broader stage of astrophysics. Pulsars, gravitational waves, and the timing of cosmic events all provide ways to test whether C, and with it alpha, has remained constant. The universe is filled with clocks and beacons, each one an opportunity to ask again whether the laws we know are unchanging, or whether they too evolve. The constancy of light has passed every test so far, but the search for cracks in that constancy continues, carried by every photon and every pulse that reaches us from the cosmos. The universe is filled with clocks. Some tick with the rhythm of atomic vibrations in laboratories. Others beat on cosmic scales, flashing across space with perfect regularity. Each of these clocks, from the smallest to the largest, becomes a tool for testing whether the speed of light and the laws it anchors are truly constant. While the cosmic microwave background and quasar spectra probe deep time, other astronomical phenomena provide ongoing, real-time checks of constancy. They are the natural experiments written into the fabric of the cosmos. Among the most remarkable are pulsars, the remnants of massive stars that ended their lives in supernova explosions. A pulsar is a neutron star, a sphere no wider than a city but denser than anything on Earth. Its magnetic field funnels beams of radiation that sweep across space as the star rotates, producing pulses that arrive with astonishing precision. Some pulsars are so regular that they rival the stability of atomic clocks. For physicists, they are more than cosmic curiosities. They are instruments, allowing the testing of relativity, gravity, and the constancy of C with exquisite sensitivity. By monitoring pulsars over years and decades, astronomers can detect changes as small as a millionth of a second in their pulse timings. If the speed of light varied across the distances those signals travel, it would distort the arrival times in ways that could not be missed. Instead, pulsars have confirmed the predictions of relativity with remarkable fidelity. Binary pulsars, in which two neutron stars orbit one another, have provided some of the most stringent tests. Their pulses arrive with a rhythm shaped by both orbital motion and the curvature of spacetime. Deviations would betray cracks in our understanding, yet none have revealed a shift in C. Another powerful probe comes from gravitational lensing, a phenomenon predicted by general relativity. When light from a distant galaxy or quasar passes near a massive cluster of galaxies, the space around it is curved, bending the path of the photons. The result is a distorted, magnified, or even multiple image of the background source. The way these images appear, their timing and alignment, depends sensitively on the constancy of light's travel. If C had varied during its journey, the geometry of lensing would betray it. Yet observations match the predictions with uncanny precision, reinforcing the conclusion that light has kept its pace steady across billions of light years. Gamma-ray bursts add another layer of evidence. These titanic explosions, unleashed when massive stars collapse or when neutron stars merge, release photons spanning a wide range of energies. If the speed of light depended on photon energy, if higher energy gamma rays traveled faster or slower than lower energy ones, then after billions of years, those photons would arrive at different times. Sensitive detectors aboard satellites have searched for such delays. None have been found within margins so tight that they rule out many exotic theories of varying C. The cosmos offers even more dramatic laboratories. In 2017, the collision of two neutron stars sent ripples through space-time itself. Detectors on Earth, part of the LIGO and Virgo collaborations, caught those gravitational waves. Just seconds later, satellites recorded a burst of gamma rays from the same event. Both the waves and the light had traveled more than 100 million years, yet they arrived almost together. The difference was no greater than a few seconds across a journey of quadrillions of seconds. This confirmed that gravitational waves and light move at essentially the same speed, within one part in 100 quintillion. It is one of the most precise demonstrations of constancy ever achieved. Each of these cosmic tests, from pulsars to gravitational waves, tightens the leash on any possible variation in C. They show that constancy is not merely a feature of our laboratories or our corner of space, but a property that holds across the universe. The cosmos itself, with its natural clocks and cataclysms, becomes the laboratory where light is tested, not for minutes or years, but for eons. And with each test, the same message emerges. Light's pace has not changed. The universe is vast, and its sheer scale provides a stage for testing constancy in ways impossible on Earth. Where laboratories can measure distances of meters and times of nanoseconds, astronomy stretches those baselines across billions of light years and billions of years. Every photon that reaches us from a distant galaxy has carried out an experiment on its way, traveling at C across unimaginable expanses. The fact that those photons arrive when and how we expect them to is itself a confirmation of constancy. Consider the dance of galaxies within clusters. These immense gatherings of hundreds or thousands of galaxies are bound together by gravity, their motions governed by both visible matter and the invisible presence of dark matter. When astronomers measure the paths of light passing through these clusters, they can compare the geometry of the bending with the motions of the galaxies themselves. The two must agree, because both are shaped by the same underlying laws of relativity. Any change in C across those vast scales would create mismatches, distorting the delicate balance between lensing geometry and dynamical motion. Yet the agreement remains, another silent affirmation that light has kept its pace. Another window comes from fast radio bursts, mysterious flashes of radio energy that last only milliseconds, but release more energy than our sun emits in days. These bursts travel across cosmic distances, dispersing as they pass through plasma in intergalactic space. The arrival times of different frequencies can be measured with exquisite precision. While dispersion from plasma is expected and accounted for, any variation in C with frequency would leave additional traces. Observations so far show no such effect, placing tight constraints on how constant the speed of light must be. Perhaps the most dramatic confirmation, however, lies in the new field of multi-messenger astronomy. When the neutron star collision of 2017 was detected, it was not only gravitational waves and gamma rays that were observed. Telescopes across the world watched the afterglow in optical light, X-rays, and radio. Each signal traveled the same vast journey, and each arrived within the narrow window expected. Had the speed of light varied even slightly with frequency or over time, the coordinated arrival would have unraveled. Instead, the harmony was perfect. The universe had delivered its messages across 100 million years, with clocks still in sync. These events do more than confirm Einstein's vision. They rule out whole classes of speculative theories, ideas that allowed photons of different energies to move at different speeds, or that permitted gravity to outrun or lag behind light, have been largely discarded. The cosmos has spoken, and its verdict is clear. Light and gravity share the same pace, and that pace has remained constant across immense distances and times. The implications ripple outward. If C were different in the distant past, it would alter not only the travel times of cosmic messengers, but also the evolution of stars, the behavior of supernovae, and the chemistry of galaxies. Astronomers compare models of stellar evolution with observations of stars billions of years old. The match is precise. Spectral lines from ancient stars align with laboratory values. The light curves of distant supernovae, used to measure the expansion of the universe, behave exactly as expected under a constant C. Once again, the evidence shows no deviation, and yet, no test is ever truly final. Each new method pushes the limits further, closing off gaps through which variation might hide. Pulsars, gravitational lensing, gamma-ray bursts, fast radio bursts, gravitational waves, each is another voice in a growing chorus. Together they tell us that if C has ever changed, it has done so by less than the tiniest fraction we can measure, a variation so small that it leaves the structure of the cosmos untouched. Astronomy thus transforms the night sky into a laboratory larger than any we could ever build. Every distant explosion, every flickering beacon, every bending of light is an experiment already performed by nature. By watching carefully, by measuring precisely, we read the results, and the results, over and over, speak of constancy. The night sky is not just beautiful, it is rigorous. Each star, each flash, each pulse is a record of natural law played out across distances and times that dwarf our imagination. The constancy of light is written into these records, and to read them is to test the very foundation of physics. By now, the message is remarkably consistent. Whether through pulsars beating with atomic precision, gamma-ray bursts blazing with unimaginable power, or gravitational waves rippling through space-time, the universe has revealed no hint that C has ever faltered. Still, the search for cracks continues. Astronomers push their instruments to new levels of sensitivity, aware that even the slightest deviation could change everything. Observatories tuned to radio, optical, X-ray, and gamma-ray bands scan the sky for transient events, hoping to catch nature in the act of something unexpected. Each new detection becomes a chance to compare signals, to see whether photons of different energies, or waves of different kinds, have traveled in lockstep. The longer the journey and the sharper the measurement, the more powerful the test. Future missions promise even greater reach. The Square Kilometre Array, a massive radio observatory under construction in Australia and South Africa, will detect pulsars and fast radio bursts with unprecedented precision. Its timing accuracy will extend the leash on constancy further still, testing whether even the tiniest discrepancies creep into signals after billions of years. Planned gravitational wave detectors like LISA, operating in space, will open a new window, capturing ripples from collisions of supermassive black holes billions of light years away. Each detection will be another opportunity to compare gravity and light, to see whether they continue to move as one. These astronomical tests are not limited to exotic events. Even the ordinary glow of galaxies provides evidence. Spectral lines from stars billions of years old match the same atomic patterns measured in laboratories today. The chemistry of the distant universe is the same as the chemistry of our own time. If C or alpha had shifted by more than the smallest fraction, those patterns would not align. The fact that they do tells us that constancy is not just a feature of the present, but a property stretching across cosmic time. The more evidence we gather, the more constancy asserts itself. And yet, the philosophical weight of the question lingers. To confirm that C has never varied is to affirm that the laws of physics are not only universal in space but in time, holding across billions of years. To find variation would be to discover that the cosmos itself is dynamic at the deepest level, that even the anchors of law evolve. In either case, the pursuit enriches our understanding. Science does not lose when variation is not found. It gains confidence in the framework that remains. So far, the balance leans heavily toward permanence. Pulsars keep their beat. Gamma rays and radio waves arrive together. Gravity and light cross the cosmos side by side, indistinguishable in speed. If C has changed at all, it has done so by less than 1 part in 10 quintillion, a stability so extraordinary that it challenges even our sense of what variation could mean. The universe has proven to be more faithful than our boldest doubts predicted. But constancy is not the end of the story. It is the beginning of new questions. Why should light move at this particular pace? Why should the constants align to allow atoms, stars, and life? These are questions not answered by evidence of constancy, but sharpened by it. The universe has not yet revealed whether its laws are the result of necessity, symmetry, or chance. The tests of astronomy close doors to variation, but they open windows onto mystery. As this chapter closes, we find ourselves at a crossroads between confirmation and imagination. The cosmos has shown us no cracks in the constancy of C, but it continues to challenge us with the possibility that new tests may one day reveal more. In the next chapter, we will explore what it would mean if the speed of light were not constant, not because we have seen it change, but because imagining such a change helps us understand just how much of physics depends on its constancy. Thought experiments illuminate what evidence has not, showing us the fragility of the structures we build upon a single number. The speed of light is not just a number in physics. It is the boundary of causality, the thread that ties together time, space, energy, and mass. Every law of modern science is built with C woven through its structure. To imagine that it could change is not to imagine a minor adjustment, like moving the hands of a clock. It is to imagine the entire architecture of reality shifting beneath our feet. Even though all evidence so far says that C is constant, thought experiments help us see how much depends on that constancy. They allow us to glimpse what would unravel if the speed of light were not fixed. Consider first the framework of relativity. Its central postulate is that C is the same for all observers, no matter their motion. If C were different for different frames, relativity would collapse. Time dilation, length contraction, and the relativity of simultaneity would no longer be consistent. The elegant geometry of space-time, in which light cones define what events can influence others, would become distorted. The very notion of cause preceding effect could falter. In such a universe, observers might disagree, not just on when events happen, but on whether one event could cause another at all. The arrow of time itself would become uncertain. Now imagine electromagnetism. Maxwell's equations, written in the 19th century, predicted that electromagnetic waves would propagate through space at a speed derived from electric and magnetic constants. That speed turned out to be C. If C were different, the balance between electric and magnetic forces would be altered. Photons would no longer behave as they do. The colors of light, the structure of spectra, the very chemistry of atoms would shift. A universe with a different C would not simply look different, it might be unrecognizable. Its atoms unstable, its stars unable to shine. The fine structure constant would also be shaken. Since alpha contains C in its definition, a change in light's speed would ripple into the strength of electromagnetic interactions. If alpha grew larger or smaller, the stability of matter would be threatened. Imagine electrons orbiting nuclei in different patterns, energy levels distorted, the absorption and emission of light altered. Chemistry as we know it might not exist. Molecules might never form in ways that allow the complexity of life. Stars might burn too quickly, or not at all, their nuclear furnaces unable to forge the heavy elements. Even quantum mechanics would feel the disturbance. Photons, the quanta of light, would carry energies linked to frequency through Planck's constant. But if C varied, the relation between energy, momentum, and mass would change. The delicate balance that allows quantum fields to knit into stable particles might unravel. A different C could mean a universe without stable protons, or without the delicate resonance that allows carbon to form in stars. The fact that we exist suggests that whatever C is, it has remained within the narrow bounds that allow atoms, chemistry, and biology to flourish. These thought experiments do not prove that C could vary. Instead, they reveal why its constancy is so central. The stability of physics is not an accident of equations, but a necessity of existence. To imagine C changing is to imagine a universe stripped of coherence, where the laws we rely on dissolve into chaos. In this way, constancy is not just a convenience for measurement, it is the condition of possibility for reality as we know it. And yet, scientists do not shy away from such speculations. By exploring what would happen if C were different, they sharpen their understanding of why constancy matters. They also prepare themselves to interpret evidence if one day variation were found. For science, advances not only by confirming what is, but by imagining what could be. If we extend the thought experiment further, the first casualty of a changing speed of light would be the coherence of relativity. In Einstein's vision, the structure of space-time is built around light cones. These cones mark the boundaries of causality, showing which events can influence which others. They define the possible futures of any given moment and the unreachable pasts of others. If C were not constant, those cones would warp unpredictably. An observer in one frame might see two events as causally connected, while another observer might see them as forever disconnected. The universality of cause and effect would dissolve into contradiction. The geometry of the cosmos would shift as well. General relativity, which describes gravity as the curvature of space-time, relies on C to link the curvature with the distribution of mass and energy. If C drifted, the way gravity propagates would change. Black holes might form differently, their horizons expanding or shrinking depending on the new rules. Gravitational waves might travel at different speeds than light, violating the harmony that has been confirmed in events like the neutron star merger of 2017. The consistency of cosmic structure would fracture. The arrow of time itself is tied to constancy. Relativity ensures that information cannot travel faster than C, preserving a consistent ordering of events. If C were variable, that ordering could fail. Some observers might witness signals arriving before their cause, others after. Paradoxes could arise, undermining the very possibility of a stable history. The flow of time, which feels so secure in our experience, would lose its anchor in the geometry of space-time. Cosmology too would be reshaped. The expansion of the universe, charted by light from distant galaxies, is interpreted through the constancy of C. If light speed were different in the past, our measurements of cosmic distances and timescales would be unreliable. The inferred age of the universe might change dramatically. Structures we believe formed under the steady guidance of gravity and light might instead have followed entirely different rules. Even the evidence for dark energy, drawn from the dimming of distant supernovae, would become suspect if C had not been constant throughout cosmic history. On the scale of stars and galaxies, the consequences would cascade. Nuclear fusion in stellar cores depends on the balance of forces mediated in part by the value of C. A slower speed of light might weaken radiation pressure, altering the lifetimes of stars. Some might collapse more quickly, turning into black holes before they can enrich space with heavy elements. A faster speed might allow stars to burn too gently, never reaching the conditions needed to forge carbon and oxygen. Either way, the chain of processes that leads from hydrogen to life-bearing planets could be broken. Even everyday experience would be altered in ways difficult to imagine. Light governs not only vision, but communication, energy transfer, and the behavior of matter itself. If C shifted noticeably, the technologies we depend on, from electronics to navigation to medical imaging, would falter. But more fundamentally, the stability of atoms would falter too, so that the very matter of our bodies might not exist in recognizable form. A universe with a different C might never have produced beings capable of asking these questions. Such thought experiments remind us how precarious existence is, balanced on the precise values of a few constants. Change them even slightly, and the tapestry of reality unravels. That is why scientists take seriously the task of testing constancy. It is not only about confirming a number, it is about confirming that the ground beneath our understanding has not shifted, that the laws we depend on are stable across the immensity of time and space. And yet, even if C has never changed, the act of imagining its variation is fruitful. It clarifies why physics takes the form it does. It highlights the interconnectedness of relativity, quantum mechanics, and cosmology. It reveals that constancy is not an arbitrary assumption, but the thread that ties the universe together. By daring to imagine its absence, we appreciate its presence all the more. When physicists entertain the idea of a variable speed of light, they are not indulging in idle speculation. They are exploring the fragility of the framework on which all of modern science rests. The exercise shows just how many domains of knowledge rely on a single principle. From the propagation of signals in fiber optic cables to the fusion reactions in the hearts of stars, C is the quiet constant that holds everything together. Its universality is not only mathematical, but existential. One of the clearest examples is the link between energy and mass. The famous relation E equals mc squared is one of the cornerstones of physics. If C were to change, the balance between energy and mass would change with it. A larger C would amplify the energy bound up in every bit of matter, making nuclear processes far more violent, while a smaller C would weaken the energy yield of stars and reactors alike. The scale of the cosmos, from the glow of the sun to the power of supernovae, would shift. Even the amount of energy required to form particles in the early universe would be different, altering the entire inventory of matter. Another domain is communication. The constancy of C guarantees that information has a maximum speed. This limit preserves causality and provides the foundation for modern information theory. If C were faster in some regions and slower in others, information could become scrambled. A message sent from one place might arrive at its destination before it was even sent, in another frame of reference. The coherence of communication, whether across computers or across galaxies, would break down. The structure of matter itself would also depend on C. The stability of the hydrogen atom, the simplest and most abundant in the universe, comes from a balance between the electromagnetic force and quantum uncertainty. Change C, and that balance shifts. Electrons might fall into nuclei, or atoms might fly apart. Either outcome would erase chemistry as we know it. Without stable atoms, there could be no molecules, no DNA, no life. The constancy of light is not simply a feature of physics. It is a precondition of our existence. This recognition brings both humility and wonder. On one hand, it shows how fragile reality is, resting on values that appear arbitrary, but are absolutely necessary. On the other, it shows how deeply our theories have captured the unity of nature. By testing C, we are not only verifying a number, but confirming that the vast edifice of physics stands on solid ground. If it ever cracked, the consequences would reverberate through every level of science. Still, the possibility cannot be dismissed. Nature has surprised us before. Constants we once assumed eternal, such as the fixed Earth or the immutability of atoms, turned out to be illusions. Science survives not by clinging to certainty, but by testing it relentlessly. If the speed of light were ever found to vary, the shock would not destroy physics, but transform it, forcing a deeper synthesis. The very collapse of one framework would herald the rise of another, more powerful one. For now, the constancy of C remains one of the most thoroughly tested principles in science. The experiments of laboratories, the signals of pulsars, the glow of the cosmic microwave background, the explosions of distant stars, all agree that light has kept its pace. And yet, by imagining what would happen if it did not, we see more clearly how much depends on it. Thought experiments remind us that constancy is not trivial but profound, the silent foundation upon which the universe builds its story. As this chapter closes, we return from speculation to reflection. Whether C has always been constant, or whether it may one day be shown to vary, its role in shaping our understanding is beyond dispute. The next step is to ask why we test these constants so relentlessly, why we challenge even the bedrock of physics. The answer lies not only in the pursuit of truth, but in the recognition that science itself is defined by the act of questioning. In the final chapter, we explore what constancy means for our quest to understand the universe, and why the drive to test it may be the most constant force of all. Every scientific journey begins with a question. Sometimes it is small, like why an apple falls from a tree. Sometimes it is immense, like whether the speed of light has always been constant. The question of constancy is not only about a number, but about the way we approach reality itself. It embodies the idea that nothing, not even the most fundamental assumption, should escape scrutiny. The act of questioning is the true constant in science. For centuries, light has served as both metaphor and measurement. It illuminates our world and defines our understanding of it. From the first attempts to measure its speed with lanterns and mirrors, to the definition of the meter based on C, light has guided our grasp of the universe. Einstein elevated it to the cornerstone of relativity. Maxwell revealed it as the unification of electricity and magnetism. Quantum theory made it a particle as well as a wave. Each step was not the end of inquiry, but the beginning of a new horizon. Today, after centuries of refinement, the evidence for the constancy of C is overwhelming. Laboratories confirm it to astonishing precision. Astronomical observations confirm it across billions of years and billions of light years. Pulsars, quasars, the cosmic microwave background, and gravitational waves all speak with one voice. Light has kept its pace. Within the reach of our instruments, C has shown no deviation, and yet, the question remains open, because science does not close its doors. We test again, not because we expect failure, but because constancy itself must be earned, again and again, through evidence. Each new generation of instruments sharpens our vision, narrowing the window through which variation might be hiding. The search is relentless, not out of doubt, but out of discipline. It is how science honors its own principles. What would it mean if C truly is constant forever? It would mean that the universe possesses laws that are not merely local conveniences, but universal truths, woven into the structure of reality. It would mean that the physics we practice on Earth is not a provincial set of rules, but a universal grammar of nature, valid from the smallest atoms to the largest galaxies. Such permanence is both comforting and profound. It tells us that across the immensity of time and space, the laws of nature have not abandoned us. But what would it mean if variation were one day found? It would not be a defeat. It would be an invitation. Science thrives on surprises. For every surprise is an opening to deeper truths. A changing speed of light would force us to rewrite our theories, to unify relativity and quantum mechanics in new ways, to search for hidden layers of reality. The collapse of certainty would be the birth of understanding. Far from diminishing science, it would make it stronger. The pursuit of constancy is therefore not about defending a number, but about cultivating humility. We measure, we test, we challenge, because we know that the universe is always larger than our grasp. Whether C is constant or variable, the deeper truth is that questioning itself is endless. The constancy of curiosity, more than any constant of physics, is the engine that drives us forward. The constancy of the speed of light is not an isolated curiosity. It is part of a wider story in which science has searched for unification, for the deep principles that connect seemingly separate domains. Maxwell's equations once unified electricity and magnetism, showing that light itself is an electromagnetic wave. Einstein unified space and time into space-time, and later mass and energy into different forms of the same essence. Each leap forward revealed that what appeared distinct was in fact connected by hidden order. In this search, constants like C play the role of bridges. They are the threads that run through different theories, tying them together. Planck's constant H unites the wave and particle aspects of matter and light. The gravitational constant G ties mass to the curvature of space. The fine structure, constant alpha, binds electromagnetism, quantum mechanics, and relativity. And C, appearing in each of these, emerges as one of the deepest links of all. If one dreams of a theory that unites all forces, one imagines a framework in which these constants are not arbitrary inputs, but necessary consequences. This dream is still unfinished. The quest for quantum gravity, the long-sought unification of Einstein's relativity with quantum mechanics, remains one of the greatest challenges in science. String theory, loop quantum gravity, and other approaches all attempt to build a bridge, and in each, constants, like C, play a central role. Whether or not these attempts succeed, the effort itself reflects a conviction that the laws of physics are not random. They have structure, symmetry, and necessity. The constancy of C is a clue to that hidden architecture. There is also a philosophical weight to this search. The existence of constants raises the question, why these numbers and not others? Why is C what it is, neither faster nor slower? Why is alpha close to 1 divided by 137 instead of another ratio? If these numbers had been different, the universe might not have produced stars, planets, or life. Some scientists see this as evidence of fine-tuning, while others suggest it may reflect a multiverse in which constants vary from one cosmos to another. We find ourselves in one where the values permit our existence because otherwise we would not be here to wonder. Yet whether by necessity, chance, or multiverse, the fact remains that these constants are real. They are written into the behavior of the universe, confirmed again and again by experiment. To test them is to engage in dialogue with nature, to ask whether the laws we see are eternal or evolving, and in that dialogue lies the essence of science. As we reflect on constancy, we see that it is not merely about physics, it is about trust. To build technology, to navigate across oceans, to launch spacecraft, we trust that C and other constants hold. To interpret the light of distant galaxies, to date the universe, to probe its origins, we trust the same. Every act of science is built on that foundation, yet trust is never blind. It is earned through measurement, renewed through testing, and strengthened by skepticism. Constancy is both a gift of nature and a responsibility of science to verify, and so the story of C is the story of our relationship with knowledge. It is the reminder that certainty is provisional, that even the deepest truths are open to question. It is the recognition that humility and curiosity are as essential as equations. Whether the speed of light is forever unchanging, or whether it hides a history yet to be revealed, the act of searching binds us together as seekers of truth. To stand beneath the night sky is to feel the immensity of the universe pressing down, and yet also to feel a strange intimacy. The same photons that left distant galaxies millions or billions of years ago now touch our eyes. They have traveled at the speed of light without faltering, carrying with them the memory of where they began. Every starlit night is a demonstration of constancy, a quiet affirmation that the laws of physics have not wavered during their journey. And still, the scientist refuses to take that affirmation for granted. Instead, the task is to measure, to compare, to test, again and again. The speed of light has been confirmed in laboratories, in satellites, in pulsars and quasars, in gravitational waves, and in the microwave glow of the cosmos itself. At every scale, in every environment, it has kept the same pace. If constancy is the verdict of nature, then curiosity is the method by which that verdict is earned. The deeper lesson is that science is not about final answers, but about continuous questioning. The constancy of C may hold forever, or it may one day be shown to change under conditions we have not yet imagined. Either way, the pursuit of the question drives progress. It sharpens our instruments, refines our theories, and expands our understanding. In this sense, the true constant is not C, but the spirit of inquiry itself. To ask about light is to ask about the universe. To ask whether its speed is constant is to ask whether the laws of nature are eternal or evolving. The answers matter, but the act of asking may matter more. For in asking, we acknowledge our ignorance, we stretch our imagination, and we open ourselves to the possibility of wonder. The story of C is the story of humanity learning not to assume, but to test, not to cling to certainty, but to seek truth wherever it may lead. And so, the journey ends where it began, with a simple question: what happens if the speed of light is not constant? The evidence says it has never changed. The imagination says we must always be ready for surprise. Between evidence and imagination lies the essence of science, and it is there that we find our place. In a universe where even the constants are questioned, perhaps the only true constant is curiosity itself. To stand beneath the night sky is to feel both the immensity of the cosmos and the intimacy of its laws. The faint light of distant galaxies, traveling for billions of years, now touches our eyes, without having slowed, without having strayed. Each photon is a messenger of constancy, carrying the memory of a universe that has kept faith with its own rules. And yet, science does not rest on faith alone. It rests on relentless questioning. We measure, we compare, we test, because even the most trusted constant must earn its place again and again. The speed of light has survived every challenge, in laboratories, in satellites, in pulsars and quasars, in the ripples of space-time itself. At every scale and every epoch, it has held firm. But constancy in science is never a decree. It is always a dialogue with nature, renewed with each observation. If C is truly unchanging, then we live in a universe whose laws are as ancient as time itself, written into the very fabric of reality. If one day it is shown to vary, then the discovery will not shatter science, but deepen it, opening the door to truths we cannot yet imagine. In both outcomes, the pursuit itself is what matters most. The constancy of curiosity, the refusal to stop asking, is what carries us forward. So we arrive at the end of our journey, and yet also at its beginning. The question that set us on this path remains: what happens if the speed of light is not constant? The evidence so far speaks of permanence, but the imagination demands that we keep testing. Between what we know and what we wonder lies the heart of science. In a universe where even the constants can be questioned, perhaps the only constant that will endure is the one we bring to it: the human drive to understand.